I'm still worried. Isn't your theory really still a wave theory?
He's worrying about the wave-particle duality that I described in lectures 1 and 2, and says, effectively, that I convinced him that it's particles in lecture 1, and then I did a lot of calculations of amplitude, which seemed to him to be nothing but the analysis of waves, which is the same kind of calculations that we do for waves. And why don't I admit that it's a wave theory that I'm really using? And I tried to explain that in 2 features about it. I chose to talk about amplitude to go from one place to another directly as a given answer. It is also possible to analyze that by saying, and I did say this, that you could think about the amplitude to go from here to here, and then the amplitude to go from there to there. And in that method of analysis, you can write it as differential equations, if you want, a mathematical form, that's the same mathematically when you're dealing with a single photon as the Maxwell equations for the wave. There are 2 differences. First, let's take the case of a single photon, in which it turns out that the calculation of my amplitudes is precisely the same mathematically as the calculation of the electric field according to Maxwell's equations, which is a wave theory. The difference is in the interpretation of the answer. The square of the electric field, for example, in that theory, is supposed to be the energy density in space. The square of the wave function, although mathematically determined by exactly the same equation, is the probability of finding a photon. So another way to answer it for the case of single photons is to say this. We calculate as if the light is a wave, but we interpret the intensity of the wave, what used to be called the energy density of the wave, not as the intensity of the light, but as the probability of finding a photon. It's that duality of interpretation which produces the difficulty, because if this were really a wave coming in, we couldn't understand how the photon counter would acquire enough energy to go off sometimes immediately when you turn it on. Nor, you see, if, for example, a wave is shining on a surface, a metal surface, we find the following, that if you shine light on a surface and you shine a lot of light, a lot of electrons come out, each one with a certain energy. If you decrease the intensity of the light, that is, weaken the waves, you would have thought that the wave would kick the electron less, and so you get a lot of electrons out with less energy. That's not what happens. You get fewer electrons with the same energy. And when your wave has gotten so weak it could hardly shake an electron at all, you still see an electron come out with a full jab of energy only once in a great while. And that paradox has to be described by not changing. You see, it would be a miracle if the mathematics would change, because nobody was going to play around with this wave theory that long if it didn't agree with experiment. So there's something right about those equations, the behavior of the amplitudes they were describing. It wasn't interpreted right. First. Second, I've talked about, not sufficiently, and this is a difficulty that many people, I answered somebody else this way, have with this wave-particle business and this quantum mechanics, is that the first thing to do when you're giving a lecture is to take the simplest example. And the simplest example is always one particle. But suppose, in the same way, we take 2 particles, 2 photons. I've talked about amplitudes for 2 photons to come to 2 points. Now, the amplitude, if you thought of it as a differential equation, is an amplitude defined. Let's take electrons, or they have 2 electrons. The amplitude defined, if you understand it, I'm writing it mathematically because you were asking me a mathematical question. The amplitude defined one particle at a position in space I'll call x1. It's a vector position. It's a 3-dimensional. And the other particle at a position x2, that's a function of time. When there's only one particle, it's a function of x, the position of that one particle, and time. Now, it's characteristic of electric fields, of fields in general, that they're functions of position and time. But when there are 2 electrons or more, the amplitude is the amplitude to find, like the probability, to find 2 electrons, one here, one there, at the time t. This kind of a function is not a wave. It's a function of 2 positions in space and time. That's a new one. When there's only one particle, it's a function of 1 position in time, then it's like a wave. When there's several particles, the functions, or the amplitudes we have to talk about, are functions of several positions in space and time. And that's not a wave in the normal sense. And so knowing that that's the case, I emphasize with a slightly different attitude, and I know I'm talking about waves if I was talking about one particle, but not if I'm talking about more. Okay?